Hello, and let's practice some bit and boolean logic operations. The bitwise logic operations we are talking about are AND, OR, XOR, and NOT. With their use, we can test, set, clear, and toggle bits. In the first task we have two variables A and R. They are both considered to be 16-bit long. If bits 1, 5 or 12 are set in the variable A, we should clear bits 14 and 15 in the variable R, otherwise we should set them to 1. This involves three main bitwise operations: bit test, bit set, and bit clear or reset. To test bits 1, 5 and 12 in the variable A, we will need a bit mask with bits 1, 5 and 12 set to 1 and all other bits set to 0. Bits are counted from right to left and from 0, so this one is bit number 0. Bit number 0 is none of the bits we want to test, so it will get 0. Bit number 1 is one of the tested bits, so it gets 1. Bit number 2, no. Bit number 3, no. Bit number 4, no. Bit number 5 is again one of the tested ones, so it's 1. Bit number 6 and 7, 8, 9, 10, 11. Bit number 12, it's 1, 13, 14, 15. We have now the binary mask. The next step is to convert this binary number to hexadecimal number, simply because hexadecimal is the only that the compiler can understand. We take the leftmost 4-bit group, it's 0001, it's easy to convert it to a hexadecimal because it's simply 1, 0000 it's 0, 0010 it's 2, 0010 it's 2. So OX1022 is the hexadecimal value for our bit mask. The next one is the mask with bits 14 and 15 are set to 1 and all other bits clear, so it's relatively easy. I put zeros everywhere apart from the bits 14 and 15. The hexadecimal representation of this value is 0x. The first 4 bits are 1100. 11 stands for 8 and 4. Together it's 12, and 12 is the hexadecimal C, and all other hexadecimal numbers are 0. At this moment we are ready to start with a bit of programming, so if you are a little bit wrong with the syntax, never mind. What we are now interested in is are the bit and logic operations. Okay, but anyway, I will try to be correct in terms of C++ syntax. So if I need to test the variable A using my 0x1022 bit mask, so for testing we need to use the AND bitwise operation. So if A and 0x1022 is anything else but 0, this means that any of these 3 bits would be set. If this is true, we need to ensure that the bits 14 and 15 in the variable R are clear, set to 0. But we have to preserve every other bit, so what I have to do here is to say that R becomes R and NOT, which is the bitwise operation for clearing or resetting bits. And I will need my mask, which is 0xC000. Otherwise, it's in C we would rather say else. R will become R, or 0xC000. To be compliant with C++ syntax, I will add semicolons at the end of both statements, but don't worry if you don't do this at the test. I will not check for exact C++ syntax. Let me now introduce a very small modification to this exercise. It will be if bits 1, 5 and 12 are all set in the variable a and everything else remains exactly the same. It won't change our bit masks, but it will change the programming part here. So the condition we have right now is checking for any bits in the bit mask to be set to 1. To check for every bit to be set to 1, I have to change this condition so that it compares directly to 0x1022. And that's all. Apart from the bitwise logic operations, we will now use Boolean logic operations. They seem to be similar. There is AND, OR, NOT, and the symbols are very similar, but they should never be confused. Boolean logic is not used to set or clear bits. Boolean logic is used to construct complex conditions. This example is a little bit more complex. This time we have to set the bit 0 in the variable r if any of the three conditions occur. Any of the three conditions suggests that we will have to use the Boolean operator OR. So let's start with if. The first condition says any of the bits 8, 9, 10, 11 in the variable a is set. So this is a classical bit test operation for which we will use the bitwise AND operator with some bit mask. We will create this bit mask as in the previous examples, writing all the bits starting from the bit number 0. The bit number 0 is none of the bits we are going to test, so it gets 0. Similarly, bit number 1, 2, 3, 4, 5, 6, 7. Now we are testing bits number 8, 9, 10, 11, and the remaining bits are all zeros. Now we have to convert this mask into hexadecimal. The first digit is 0, 1, 1, 1, 1 is F, 0, 0, and this value should be any of the bits is set, so should be not equal to 0. But actually in C++ and C and Java and any similar language, the Boolean logic works in this way that any expression not equal to 0 is considered as true. So actually we can delete these characters here, and the value of a and 0x0f00 will generate the logical true in case if it is not equal to 0. So it's exactly what we want to achieve. We will now go on to the second condition, but we need to connect the two conditions using the Boolean operator OR. The second condition is 0th bit in the variable a is 1, and at the same time bits 0, 1, 2, 3 in the variable b are all 1. It is by itself a complex condition, and the words at the same time suggest using the Boolean operator AND. The first sub-expression says 0th bit in the variable a is 1, so it's again a classical bitwise test with a very simple bit mask, which would have just 0 bits and set to 1. So actually this will do. That's the first sub-expression, and the second sub-expression will be connected with a Boolean operator AND. The second sub-expression is about the variable b and its bits 0, 1, 2, 3. So it's b and 0x, and now let's create the bit mask. Bits 0, 1, 2, 3 are here. I don't need any more digits because leading zeros are insignificant. I can add as many zeros as I want in the beginning of any number, but they will have absolutely no significance. So this is b and 0xf. It is the test for bits 0, 1, 2, 3, but they are all to be equal to 1, so I actually need to compare this expression to 0xf. We are now left with the last condition. Bit 2 or 15 in the variable b are clear. So once again we will connect this condition using the Boolean operator OR of the variable b and 0x. And now let's create the bit mask. This is bit 0, 1, 2. And the only other bit that we are interested in is bit 15, which is here. All other positions are zeros. Okay, so this particular mask will be 8004. This condition here would be good for testing if any of these two bits, 2 or 15, are set to 1, but our condition says about the bits to be clear. So we could actually try something like this. I have to scroll this a bit. But this is of no good either. This condition actually checks for both bits in the same time and would only be true if both bit number 2 and bit number 15 were clear. Our condition says bit 2 or bit 15, so this is wrong. Let's have a closer look at various conditions we could have. The most common of these conditions, which is exactly the same as this, is true if any bit in the bit mask is equal to 1. This condition is the negation of the previous one, and it's only true if all bits in the bit mask are equal to 0. This is another useful form that we have already used today. It is true only when all the bits in the bit mask are equal to 1. And this condition is again the negation of the previous condition. It is true if any bit in the bit mask is equal to 0. This means bit 2 or bit 15 is clear, so this is exactly what we want to achieve. So I will copy this condition here. So this is now the complete conditional statement for our example here. We only need to set the bit 0 in the variable b to complete entire exercise. Thank you for watching.